For decades, the story of Europe seemed settled. Farmers arrived from the Near East, spread across the continent, and within a few centuries, the people who had lived there for tens of thousands of years, the hunter-gatherers, were gone. Absorbed, replaced. Their genes diluted to almost nothing. Study after study confirmed it. The DNA was clear. Farming did not just bring new crops, it brought new people. And those new people, almost everywhere in Europe, became the majority within a few generations. But a strip of land along the coast of what is now the Netherlands and Belgium tells a different story. A place where dark-skinned, blue-eyed foragers, people who looked nothing like the Europeans we imagine today, held on for thousands of years longer than anyone thought possible. And what ancient DNA has revealed there does not just challenge the consensus. It unravels the entire timeline and connects to one of the most dramatic population replacements in all of human history. Imagine Europe around 6,500 years before the Common Era. Farmers from Anatolia, modern-day Turkey, are pushing west and north. They carry domesticated wheat, barley, sheep, cattle, and they carry distinctive DNA, traceable across thousands of miles. Wherever they settle, the genetic signature of the local hunter-gatherers fades. In Central Europe, the turnover is swift, 70 to 100% of the ancestry replaced. In Britain, Neolithic farmers arrive and the old forager lineages shrink to almost nothing. In Iberia, the same. In Scandinavia, a similar pattern. The broad story, confirmed by hundreds of ancient genomes, is one of replacement. Not coexistence, not blending. Replacement. The sheer scale of this turnover shaped how archaeologists read every site in Europe. When pottery styles changed, it meant new people had arrived. When burial practices shifted, it signaled a new population. And when the Second Great Migration came, around 3000 BCE, steppe pastoralists from what is now southern Russia pushing westward with horses and bronze, the pattern repeated. New people, new genes, old populations pushed aside. This was the framework. 3 ancestral layers stacking neatly across the continent. Hunter-gatherer on the bottom, Neolithic farmer in the middle, steppe herder on top. It was elegant, it was supported by data, and it left almost no room for the people who came before. But there was a region where the archaeology never quite fit the model. Along the lower reaches of the Rhine and the Meuse, where rivers split into a maze of channels and empty into the North Sea, the landscape is different. Wetlands stretch between forested dunes. Peat bogs blanket the lowlands. Tidal flats give way to marshes, thick with fish, migrating birds, otters, beavers. This delta was once the eastern edge of Doggerland, that vast landmass now submerged beneath the North Sea, which, until around 5500 BCE, connected Britain to the continent and served as perhaps the richest hunting ground in all of the Mesolithic Europe. When Doggerland drowned, its people didn't vanish. They moved to higher ground, to the dunes and levees of the Rhine-Meuse delta. And there they stayed. Archaeologists working these waterlogged sites kept finding something unusual. Communities here had adopted pottery, yes. They kept some cattle. They grew a few crops. But the bulk of their diet came from pike, waterfowl, wild plants, deer. Their settlements sat on river levees and raised sand ridges surrounded by water. They built 5.5-meter canoes from limewood. They carved paddles from oak. They wove nets and set fish traps from wicker and bone. They hunted otters and beavers for pelts in winter. They were, by every practical measure, still living like hunter-gatherers, thousands of years after farming had taken hold everywhere else around them. These people looked different from modern Europeans, too. Ancient DNA from hunter-gatherers across Western Europe, from Cheddarman in Britain to La Branja in Spain, tells us they typically had dark brown to black skin and striking blue or blue-green eyes. They carried none of the genetic variants for lighter skin that later arrived with Neolithic farmers. They got their vitamin D from fish and game, not sunlight through pale skin. They were robust, adapted to cold, and shaped by a diet no farmer would recognize. The question was whether this was cultural conservatism, people choosing to keep old habits, or something deeper, something genetic. Previous studies could not answer it because the evidence was difficult to recover. Bones dissolve in acidic peat. Skeletal remains from wetland sites are rare and poorly preserved. Many of the most important sites lie 5 meters or more below the modern surface, buried under layers of clay and flood sediment. The handful of ancient genomes available from this region were too few and too scattered to show a pattern. Researchers could see the archaeology suggested persistence, but they couldn't prove whether these were the same people, genetically, or newcomers who had simply adopted a foraging lifestyle in terrain that didn't suit farming. There was another problem, too. The entire field of ancient DNA in Europe had been built on a model of replacement. When you go looking for evidence of turnover, you find turnover. The broad brush picture, 3 ancestral layers neatly stacking, worked so well across dozens of regions that it became the default. Nobody was asking where it might fail. Nobody was looking for exceptions. And the one place where an exception was most likely to exist, a waterlogged delta with poor bone preservation and few excavated burials, was exactly the place where the data was hardest to get. The tools to answer the question required something that only became possible in the last decade: the ability to extract entire genomes from degraded bone fragments, often from the dense petrous bone of the inner ear, the single best source of ancient DNA in the human skeleton. In sterile clean rooms, wearing full protective suits to prevent contamination, technicians grind these tiny bone fragments to powder. Chemical baths strip away millennia of microbial invasion. What survives, if anything, are threads of genetic code so fragmented that only machines built to detect signal within noise can read them. In 2026, an international team led by Inigo Olalde of the University of the Basque Country and David Reich at Harvard published their results in Nature. They had assembled genome-wide data from 112 individuals who lived in the Rhine-Meuse region between 8,500 and 1,700 BCE. The dataset spanned nearly 7,000 years, from deep in the Mesolithic through the Neolithic and into the early Bronze Age. It included the first genomes ever recovered from the Swifterband culture, the semi-agrarian communities of the 5th millennium BCE, who had long puzzled archaeologists. And for the first time, researchers could track what happened to the hunter-gatherer gene pool in this one specific region, generation by generation, across the entire transition. Before we see what this evidence revealed, if this kind of discovery fascinates you, subscribe so you don't miss future stories like this one. What appeared in the data was unlike anything seen anywhere else in continental Europe. While the rest of the continent showed hunter-gatherer ancestry collapsing within centuries of the farmer's arrival, here it held, at approximately 50%. Not for a few generations, for 3,000 years. From roughly 4,500 BCE, when farming first reached the region, all the way to around 2,500 BCE, the local population retained a level of forager ancestry that had vanished everywhere else a millennium or more earlier. 80 generations. That is how long these communities maintained a genetic signature that the rest of Europe had lost. And the mechanism was specific. The researchers looked at the Y chromosome, inherited father to son, and at mitochondrial DNA, inherited through the mother. The Y chromosome lineages remained overwhelmingly hunter-gatherer. The mitochondrial lineages, though, showed something else. The small amount of farmer ancestry that did enter the population came almost entirely through women. Farmer women marrying into hunter-gatherer communities, bringing with them knowledge of crops and animal husbandry, but not displacing the local men. This was not conquest. It was not replacement. It was selective adoption, driven by individual choices, family alliances, and the practical reality that a wetland full of fish and game does not force you to become a farmer. So what does this rule out? First, coincidence. A 50% forager ancestry proportion holding steady across dozens of individuals from different sites across 3,000 years is not random. It reflects a stable population structure maintained across generations. Second, cultural imitation without genetic continuity. These were not newcomers who happened to fish. Their DNA proves they descend from the same lineage as the Mesolithic foragers who had lived there for thousands of years before farming existed in Europe. Third, the clean replacement model. In every other well-studied region, the arrival of farming meant the rapid genetic eclipse of local hunter-gatherers. Here, it did not. The environment, a landscape of water and marsh unsuited to the intensive cereal farming of the Loess Plains to the south, created a buffer. The wetlands protected a way of life and a genome that everywhere else was erased. And what this implies is profound. These weren't passive holdouts clinging to a dying lifestyle. They were communities sophisticated enough to take what they needed from the incoming culture, pottery, some farming techniques, some livestock, while maintaining their own identity across a span of time that dwarfs most civilizations. But the story does not end with survival. It ends with expansion. Around 2500 BCE, something changed. New groups associated with the corded ware complex arrived from the east, bringing steppe ancestry. In much of Europe, this was the second great replacement event. But in the Rhine-Meuse lowlands, even this wave was absorbed differently. Locals adopted corded ware pottery without gaining significant steppe DNA. The genetic continuity held again. Then came the fusion. The Rhine-Meuse population, still carrying its ancient forager ancestry, mixed with incoming corded ware migrants to form something new, a hybrid population, genetically, culturally, technologically blended. This new group adopted a distinctive bell-shaped drinking vessel, elaborate burial practices, copper tools, and archery equipment. Archaeologists call them the Bell Beaker people. And the DNA shows that they carried 13 to 18% of their ancestry from those stubborn wetland foragers. What happened next is one of the most dramatic demographic events in European prehistory. Around 2400 BCE, these Bell Beaker groups crossed the North Sea and entered Britain. Within a few hundred years, approximately 90% of Britain's existing gene pool, the Neolithic farmers who had built Stonehenge, the people who raised the great megaliths, was replaced. The Y chromosome haplogroup R1b, previously absent in Britain, suddenly appeared in over 90% of male individuals. The builders of Stonehenge were gone, and the people who replaced them traced part of their ancestry back to the fishermen and foragers of the Dutch swamps. Not everyone agrees on the mechanism. Some researchers point to a plague that swept Europe around 2800 BCE, possibly weakening Neolithic populations and giving the Bell Beaker groups a demographic edge. Others emphasize that steppe-descended populations may have had advantages in animal husbandry, able to rely on milk and meat, producing more surviving children per generation. Even a small fertility advantage, just a couple more children reaching adulthood per family, can produce near total demographic replacement within a few centuries. The Y chromosome evidence in Iberia, where male lineages were almost completely replaced while female lineages persisted, suggests something darker in some regions, patterns that raise difficult questions about violence and exclusion. And the Rhine-Meuse story itself is not without tension. The data shows that for over 1,500 years, farmer women married into forager communities. But what happened to the forager women? Were they marrying out? Were they choosing to stay? The DNA can trace ancestry, but it cannot trace motive. The sex bias in the genetic record, fathers from the old world, mothers increasingly from the new, describes a pattern. It does not yet explain why the pattern held so consistently, or what social rules enforced it. What remains unresolved is exactly how the Bell Beaker identity formed. The bell-shaped cup itself originated among Neolithic farmers in Iberia, people with no steppe ancestry at all. How and why that pottery style was adopted by a genetically distinct group in the Low Countries, hundreds of kilometers to the north, is still unclear. Culture and genes do not always travel together. Sometimes ideas move faster than people. Sometimes people carry ideas they didn't invent. Today, somewhere in the mud of the Rhine Delta, 5 meters below the surface, the remains of that older world are still preserved. Limewood canoes, antler harpoons, woven fish traps, the bones of pike eaten around winter fires, and in those bones, when the chemistry is right, fragments of DNA that connect an 80-generation chain of fishermen to the people who reshaped Britain. If this hidden chapter of Europe's past intrigued you, subscribe to explore more stories that the evidence is only now revealing. Here is what the genetics ultimately tell us. The longest surviving hunter-gatherer population in all of Western Europe didn't fade into irrelevance. It became the seed of a culture that transformed the continent. The people the history books forgot are, in part, the ancestors of modern Britain. So if Europe's ancient foragers survived for 3,000 years in a landscape everyone else abandoned for farmland, what else might the DNA in Europe's waterlogged, overlooked, and submerged sites still be hiding?